program is a set of instructions written in a programming language that a computer follows to perform certain tasks. One of these programming languages is Java, an object-oriented programming language. Objects are designed through classes and methods. To create a class, type public class name. Execution of a program begins at the main method, located inside your class and written as public static void main string bracket args. While a program is running, it is in runtime. For a program to print out a value, type system.out.print, open parentheses, what you want to print out, and then a close parentheses followed by a semicolon. If you are printing text, the text must be in quotes. You must add a semicolon after each command or statement. To print out a value and add a new line afterward, use system.out.println instead. The compiler's job is to take our human-readable code, check it for errors, and then translate it into machine code for the computer. The compiler may check for syntax errors and errors from the structure or arrangement of the code. Programmers use comments to annotate their code, typically done with a double slash. A variable is a name associated with a memory location within a computer, which can store a varying value.
A bit is either a 0 or 1 that can represent all sorts of values in computing. Primitive variables set aside just enough bits in memory for a primitive type. There are 8 primitive types. Booleans only have 1 bit and 2 possibilities, true and false. There are 5 integral primitive types, but let's focus on 4 of them for now. These 4 are all non-decimal numbers, but where they differ is the range that they can use. A byte is the smallest of these. Containing only 8 bits, they have a range of negative 127 to 127. A short has a range of about negative 32,000 to 32,000. An integer a range of about negative 2 billion to 2 billion. And a long a range of about negative 2 to the power 63 to 2 to the power 63. There are 2 floating point primitive types, double and float. They both represent decimal values, but where they differ is the accuracy of the decimal. A double is the more accurate of the two, with 15 to 16 decimal digits of precision, while floats only have 6 to 7. However, a float is only half the size of a double, at 32 and 64 bits respectively. The final integral primitive type is called a character. It is a single 16-bit Unicode character. You can store any of the 65,535 characters in the Unicode database, but only a single one. While it can be a number, it can also be a letter or even a symbol. While not technically a primitive type, strings are a collection of characters. Because of the built-in support and importance of strings, simply add quotations to text to make it a string. Many consider them to be the 9th primitive type.
To create a variable, type in the variable type, followed by the variable name, then an equal sign, and then the value. Declaring a variable is just typing a variable type and name, while initializing it requires a value assignment as well. Adding the keyword final before the variable type ensures that the value is unchangeable. The assignment operator or equal sign enables a program to initialize or change the value stored in a variable. The value of the expression on the right is stored in the variable on the left. The arithmetic operators, which work on integers and doubles, consist of addition, subtraction, multiplication, division, or modulo, which is the remainder after dividing two numbers. Multiplication, division, and modulus have precedence over subtraction and addition. Operations can be shortened with compound assignment statements, like variable name plus plus, which adds 1 to the variable name. When performing integer division, Java truncates the decimal resulting from the division. To avoid this, cast one of the variables to a double to produce a double result. To cast a variable, put the desired variable's type in parentheses, followed by a number or variable name. Doubles may be cast to ints where the decimal value is truncated. Objects are values in a program that implement data to model a real-world or imaginary concept. They are essentially what you program or what does the work in your program. Classes create and shape objects as a cookie cutter does to a cookie. An object created by a particular class is said to be an instance of that class. Objects have attributes or features and properties that define them as well as behaviors. Attributes are called instance variables, and behaviors are called methods. To create an object of type class name, type class name object name equals new class name parentheses. The keyword new requests the memory required to store an object's data. The object's name serves as a reference to the object in the computer's memory. An object that is only declared or set to null has a variable that could function as a reference, but doesn't because the object isn't initialized. Null pointer exceptions arise when trying to reference a null object. When creating objects, classes have constructors that initialize the attributes of an object. The constructor signature is written as public class name, and in parentheses, the parameter list. The parameter list is a list of the type of values being passed and a variable name to denote them, also called the formal parameters. When an object is created, specific values called the actual parameters, or arguments, written in the parentheses following class name in an object's initialization, replace the formal parameters and initialize an object's attributes. Methods are the instructions that define the behavior of a class. To use an object's method, type the object's name .method name. The dot operator basically asks the object to perform the specified method. Object methods, or non-static methods, can only be called in an object of the same class the method is in and work with the attributes of an object. Methods in the same class call each other with method name parentheses. To call non-static methods in another class, you must create a new object and then call the desired method on the object. Methods interrupt statement execution, as once a method is called, all statements within the method execute before the initial execution resumes.
Methods may also have parameters being called with the syntax object.method parentheses arguments. Note arguments indicate we are passing in actual parameters that replace formal parameters. Void methods do not return any values and may manipulate the attributes of an object. Non-void methods do return a value like an int, double boolean, or so on. Non-void methods may have certain parameters that can be passed into calculations. The result is returned using the return keyword. Once a value is returned, the method stops. Strings are objects that are a sequence of characters and can be concatenated using the += operator. To add quotes or backlashes to a string, use the escape sequence. Strings are ordered by indexes, the first character being index 0, while the last one being string length -1. String methods don't change the actual string, but make a copy of the string and then modify it, as strings are immutable. Some common string methods include string.length, which gets the length of a string, string.equals_other string, which determines whether one string is the same as another, and string.substring x, y, which creates a new substring starting at index x and ending at index y -1. Sometimes integers and doubles must be autoboxed into wrapper classes, which create objects from primitive types. The reverse of autoboxing is unboxing. The math class contains static methods that help perform various operations like generating random numbers, which may be done using the generic formula. For a range with a minimum min and a maximum max, to generate a random number from min to max inclusive, use int random equals cast to int, open parentheses math.random times range close parentheses plus min, the range being max minus min plus 1.
Boolean variables are expressions that have either true or false values. Primitive values or object references may be compared using relational operators like equals, not equals, greater or less than, and so on. When considering object references, the equals operator tests if they reference the same object, not if the properties of the object are the same. To test whether the attributes of two objects are the same, use the .equals method. Classes have their own equal methods for their particular instances to determine if a reference is null, compared to the keyword null using the double equals operator. Boolean expressions take variables and compare them with relational operators. If statements, which fall under the broad name of conditionals, change the flow of program execution by evaluating a Boolean. If a Boolean is true, then the statements under the if statement occur. Otherwise, the code skips the if statement. The safest notation for an if statement is if open parentheses Boolean statements close parentheses open curly brace, then your regular statements followed by a close curly brace. For a single regular statement, curly braces aren't required. There are no semicolons at the end of the Boolean expression. For two-way selection, use an if-else statement. If a particular condition is true, then the if statement will execute, or else the else statement will execute. The notation for an if-else statement is the same as the if statement, but after the if, write else, open curly brace, statements, and close curly brace. You may also use a one-line else statement, but be careful. If you are using nested if statements and have a dangling else statement, it will merge with the closest if, which may mess with the functionality of your program.
Multi-way selection for conditions when evaluated has multiple possible outcomes. This is done through the else-if statement, the else-if being between the if and else. If a certain condition is true, execute these statements, or else, if these conditions are true, do these statements, and so on, or else if none of these conditions have been met, do these statements. An else statement can have many else-ifs, the notation being the same as an if-else statement, but between the if and else, add else-if booleans with statements between your curly braces, just like an if block. Sometimes multiple or particular conditions need to be met to trigger an if statement, so to help condense these statements, logical operators are used. Logical operators enable us to produce new booleans by evaluating multiple booleans together. The AND operator, notated with two ampersands, determines whether two booleans are true, and if so, returns true and otherwise false. The OR operator, noted with two vertical bars, returns true if one of two booleans is true and false otherwise. The NOT operator, notated by an exclamation mark, flips a boolean value. The NOT of true is false, and the NOT of false is true. De Morgan's laws are transformation rules that help us simplify complex Boolean expressions. Its most straightforward application is as follows. The NOT of Boolean A evaluates to the opposite value of Boolean A. The NOT of AND evaluates to OR. The NOT of OR evaluates to and so on. The NOT of greater than evaluates to less than or equal to, and vice versa. The NOT of less than evaluates to greater than or equal to, and vice versa. To apply De Morgan's laws to complex Boolean statements, use the distributive property.
Iteration is a way to loop one or more statements without having to repeat code. Java contains many different types of iteration, the most common of which is a while loop. A while loop continuously executes the statements contained within it as long as the associated Boolean condition is true. To create it, one must type while parentheses condition close parentheses. Once the condition is false, the loop finishes and the statements that follow the loop continue to be executed. In essence, the while loop is similar to the if statement except it repeats. While loops are written when the condition being evaluated may loop an unknown amount of times. Another common type of loop is the for loop, which is normally used when you know how many times you need to loop something. Creating a for loop requires 3 steps, the first 2 separated by a semicolon. Type for open parentheses variable type var name equals loop start value semicolon, then your Boolean condition followed by a semicolon, and then var name plus equals your incrementation amount, close parentheses. You can decrement or increment your loop variable, as well as use the plus plus or minus minus operators. When tracing iteration, the Boolean condition in the loop header is first evaluated. If true, the loop completes an iteration, and then your loop variable is changed. This is done until the condition becomes false. One useful application of loops is traversing strings. Common string algorithms with loops include removing certain letters from strings or reversing a string itself. Certain algorithms require using multiple levels of iteration. We can use nested loops to have a loop executed inside of another loop. When one loop is nested in another loop, the outer loop determines if its own Boolean condition is true, and if so, the inner loop executes if the inner loop's Boolean condition is true, and then the condition in the outer loop is evaluated once again, and this process repeats until some stopping point. Essentially, we are looping a loop. This is pretty useful for data sorting or 2D arrays. When tracing loops, creating a table and keeping track of your loop and extraneous variables is helpful to avoid getting lost in a slew of code. When dealing with nested loops, a trick to determine how many times the statements within the inner loop would execute is to multiply the number of times the outer loop executes by the number of times the inner loop executes.
Avoid one-off errors by ensuring your conditions meet the right criteria and your loop variables are properly initialized and have the correct stopping point. When writing while loops, double-check your conditions to avoid infinite loops which may crash your program. To perform an iteration first without evaluating the condition, use a do-while loop. The notation for this is done by typing do, open curly braces, loop body, close curly braces, and then to the right of the curly brace, type while parentheses condition. Do while loops first perform the iteration, then evaluate the condition, and if true, the iteration continues. Input controlled loops take user input and use it to start or stop the loop. Java packages are a pre-written group of classes imported into a program, so programmers don't waste time writing existing classes. To take user input, use the java.util package, which is imported in the very first line of a program by writing import java.util.*. Input is taken through objects called scanners. To initialize a scanner, write scanner name equals new scanner parentheses system.in close parentheses. Input types can be primitive types or strings. To actually take the input from the user, in the next line, write var type input var name equals scanner name dot next var type. For strings, this is next line. This input variable's usage varies depending on the functionality of the program. You can structure an input controlled loop so that when a user enters a particular value, the loop exits.
Objects are values in a program that implement data to model a real-world or imaginary concept. They're essentially what your program makes or what does the work in your program. Classes create and shape objects, like a cookie cutter does to cookies. The first step to writing a class is creating the class header, which is written as public class name. There can only be one public class in a file, and the public class's name must match the file's name. Note that all words in the class name are capitalized and have no spaces in between them. All variable and method names should be in camel case. Most importantly, ensure you indent your code so it's actually readable, which is especially convenient if you encounter errors. The general structure of a class is as follows. The class header, the instance variables or attributes, the constructors, and the methods or behaviors of whatever object will be created. After writing the class header, begin with declaring your instance variables. To declare instance variables, write private or public if you need to, var type, var name. The keywords before the var type indicate the scope of the variable, or where this variable can be accessed. If the variable is public, it can be accessed outside of the class, and if it is private, it may be accessed only within the same class it is declared in. We are encapsulating our variables.
Data encapsulation is the process of keeping the implementation details of a class hidden to better maintain the integrity of data within the program, and it is a fundamental principle of object-oriented programming. It ensures that sensitive data can remain in a class while the methods that the sensitive data is a part of can still be executable in a different class. Note that while we usually only keep our instance variables private, methods and constructors may also be kept private. Constructors initialize an object's parameters and can be written with them, the typical constructor signature being public class name, open parentheses, parameter list, close parentheses. The parameter list passes values for the initialization of a constructor. Constructors ensure an object is in a valid state where instance variables have values that can be implemented in the object's public method. You can put any number of parameters into a constructor given that you have created one that processes those parameters. Having multiple constructors is called overloading the constructor. Based on the specific order, including specific variable types, of the parameters of your constructor, you can have any number of constructors. Make sure that the parameters for each of your constructors are different from the rest, however. When no constructors are written, Java will create a no-argument constructor that initializes instance variables to default values, zeros for ints and doubles, false for booleans, and null for strings. You may also overload the no-argument constructor and replace it with your own, provided that there are no parameters for that constructor.
It is important to document code when developing large projects. To write one-line comments, type 2 forward slashes. To write multi-line comments, write a forward slash and asterisk on the first line of comments, and an asterisk followed by a forward slash on the last line of comments. In code documentation, you may see preconditions and postconditions. Preconditions are the requirements for a particular section of code to execute. Postconditions are the requirements for what results from execution. Sometimes, we want to access private variables in outside classes. Getter methods return a copy of private variables and are written as so: public var type get var name, parentheses. Recall that methods use the return by value process. Methods will give a copy of the primitive type they are handling, and when dealing with reference types, give a copy of the reference variable. The toString method allows us to print useful information about an object and is written as follows: public string, toString parentheses. And within the curly braces of the method, return a string we want to be printed out when you print the object using system.out.print. If you do not have a toString method explicitly written, the object will not be printed the way you want it to be. To change the value of instance variables outside of the variables class, use setter methods. The setter method takes the value of its parameter and sets the instance variable in its class to the given parameter. The general format for a setter method is public void set var name, in parentheses, var type, followed by the variable's new value, followed by curly braces, var name equals new value. Note that the method does not have a return type. There is no need to return the instance variable, which is really the job of a getter, so the setter method remains void. Methods allow for procedural abstraction, the process of reducing the complexity and repetition of code, increasing the efficiency of programs, and it's a fundamental principle of object-oriented programming. The method definition first consists of the method's signature, scope type, public, private, etc., followed by the optional static keyword, followed by the return type, int, double, string, etc., followed by the method name, and then followed by, in parentheses, the method's parameter list. The second part of the method definition is the method body, which is under the method header and contained in curly braces. Methods are found by their headers, and what they do is contained in their bodies. To call an object's method, type the object's reference name followed by .method name parentheses. Methods may have formal parameters that contain variable types and names that are set to the actual parameters passed into the method. The values in the argument must correspond to the order of the parameters. When primitive types are passed as arguments, the formal parameter is initialized with a copy of that primitive value, and hence the original primitive type will remain unaffected by whatever is done to the copy of it in the method. This process is called value semantics. When a reference type is passed as an argument, the formal parameter is initialized to a reference type of the same object, and thus both reference types are aliases of each other, and therefore the method can change the actual object whose reference was passed as an argument. This is called reference semantics.
Static variables and methods belong specifically to a class. Non-static variables and methods belong to any instance of a class. For example, a bird object might have the attribute blue associated with it, and because this color variable belongs to a specific instance of some bird class, this variable is non-static. A static variable or method can't access non-static variables or methods because static is class-bound and non-static types can vary from object to object. Static variables could be useful for counting the number of instances a class has, and static methods are useful for methods all objects could perform the same way, like in the math class. You don't need to create a math object every time you want to perform a math operation using the class's methods. Instead, you call static methods by typing class name.static method name parentheses. The scope of a variable is where that a variable is accessible in a program. Local variables are declared within a block of code, like constructors or methods, and are only accessible within that specific block of code. Unlike instance variables, these variables cannot be public or private. Note that since local and instance variables have different levels of scope, make sure that you don't try to access local variables outside of where they were declared. In other words, don't treat it like it has a class level scope, in which case the variable can be used by the entire class. This is because local variables don't have access to all parts of a class. Because formal parameters have the scope only available to their constructor or method, they can be referred to as local to their own constructor or method. The this keyword is used to refer to the current instance of an object that has been called by the program. Typically, when using the this keyword, you access the attributes of the current instance by using this.instance variable name. One important note is that you should use this dot on instance variables rather than on local variables because local variables aren't related to the attributes of a class, only to a specific block of code.
Arrays are a data structure, a collection of related data within a program. Arrays are a block of memory that store related data elements of the same type, each of these data elements being marked by an index within an array. Arrays are essentially lists of values that cannot change the number of values they hold once initialized. All data elements are kept under the array's name, and they may be primitive types, strings, or other objects. The index is the location of an element in the array, the first element being at index 0 and the last element being at index array length -1. Arrays are objects, so one way of initializing them is using the following format. var type open square brackets, close square brackets, array name equals new var type open square brackets, integer length of the array, close close square brackets, followed by the usual semicolon. Once the array is created in memory, the size of the array can be changed. More specifically, an array's length's instance variable is declared as public final int. Public means we can access it by typing arrayname.length. Note, this just shows us the variable, it's not a method like string.length parentheses. And final means the value cannot change after creation. To access individual elements of the array, type arrayname open square brackets index of element close square brackets. From here, you can set this element to a specified value. If you have all the values in your array predetermined, instead of modifying every single value, you can initialize an array using an initializer list. To set the values in an array during its initialization, type var type square brackets array name equals open curly braces and then each value or reference separated by a comma, closing the list with a close curly brace and ending with a semicolon.
When you create an array of some primitive type or reference of length x, there are x spaces in memory reserved for those x number of primitive types or references. When those x values are initialized, those spaces in memory store those values. When they aren't initialized, like when you use the new keyword but reserve the space in memory, the elements in the array are set to the default values of the array type, which is null for strings, 0 for ints, 0.0 for doubles, and false for booleans. Traversing an array is using a loop to visit the elements of an array and perform operations on or with them. To visit each element in an array using a for loop, note we will use I as our index variable. Type for open parentheses in I equals 0 semicolon I is less than array name dot length semicolon I plus plus close parentheses, followed by curly braces that contain what you'll do with the array. Because I represents the index of the array, to access a particular element, you need to write array name square brackets I instead of the index variable. This is a powerful example of data abstraction, as we can represent multiple indexes by one variable, simplifying the complexity of our program. You can start the loop anywhere in the array or traverse the array in reverse by manipulating your loop variable accordingly. This is all depending on why you traverse the array.
Common array algorithms include computing sums/averages of elements in an array, searching for particular elements, determining if one or all elements have a particular property, shifting elements right or left, reversing elements, accessing consecutive pair of elements, checking for duplicate elements, and sorting arrays. Enhanced for loops are specialized loops for arrays that do not use an index variable. They are useful for reducing program complexity and are written as for open parentheses, var type, item name, colon, array name, close parentheses, followed by curly braces containing the statement using the array elements. For each iteration, the item or value being used in the for each loop is a copy of the actual data element of the array, and hence for each loops cannot actually modify the elements of the array it traverses. Note that for any for each loop, it can also be written as a regular for or while loop. Use for each loops when you need to access all elements of an array, don't need the index, and don't need to change any values in an array.
Exceptions are events that disrupt the flow of execution in a program. An array index out of bounds exception occurs when trying to access an index outside of the array's length. Null pointer exceptions occur when trying to reference a null object. It's like trying to use something that doesn't exist, thus an exception is thrown. An arithmetic exception occurs when trying to perform undefined mathematical operations like dividing by zero. When an exception occurs within a class or method, that class or method creates an exception object that can actually be caught using the try-catch block. The general notation for a try-catch block is written as follows: try, open curly braces, code that may throw an exception, close curly braces, followed by catch, open parentheses, exception type, exception object variable name, close parentheses, followed by curly braces that contain the code to handle the exception. There can be multiple catch blocks that deal with different types of exceptions from the try block's execution. One way of handling exceptions is to get the exception message, done by typing exception object variable name .get message parentheses. This will display the exception's message like a print line. An optional block that can be added to the try catch block is the finally block, which is written as finally curly braces that contain code that will execute regardless of whether an exception is thrown or not. Arrays are resizable arrays. Unlike arrays, their length can be changed. Elements may be removed from, added to, or changed in ArrayLists. The ArrayList class must be imported within the java.util package. Recall that importing a package imports a set of related classes into your program. To begin initializing an ArrayList, type import java.util.* semicolon into the very first line of your program. To initialize an ArrayList of type var type, write ArrayList less than symbol var type greater than symbol ArrayList name equals new ArrayList less than symbol var type greater than symbol parentheses followed by the usual semicolon. Optionally, if you want to convert an array called array name to an array list, inside the end parentheses of the initialization, write arrays.asList open parentheses array name close parentheses. If you don't specify the ArrayList type, the type defaults to object. ArrayLists can only hold object types, so there aren't any primitive type ArrayLists. It is better to specify the type of an ArrayList to prevent runtime errors that occur while the program is executing. Attempting to get the size of a declared ArrayList results in a null pointer exception. The size of a newly initialized ArrayList is 0. To create an ArrayList that holds ints or doubles, the ArrayList should hold the wrapped version of the primitive type. Primitive type integers will be autoboxed into integer objects, and primitive type doubles will be autoboxed into double objects. To find the size of an ArrayList, write ArrayList name.size parentheses. Note that the array uses dot notation with the arrays field, while the ArrayList uses a method called size.
To add an object to an ArrayList, write ArrayListName.add in parentheses the object you want to add. If you add a primitive type like int, the integer will be autoboxed into its integer wrapper. When you want to add an object at a specific index, write ArrayListName.add in parentheses the desired index, comma, the object you want to add. To remove an element from a specific index, write ArrayListName.remove in parentheses the index number of the element to be removed. The remove method returns the value that was removed, shifts all elements after the removed element to the left by 1, and decreases the list length by 1. Just like with arrays, the ArrayList index starts at 0 and ends at list length -1. The ArrayList class has its own getters and setters. ListName.get open parentheses I, close parentheses, returns the object located at index I of listName. To replace an index with another value, write ListName.set in parentheses the index of the element to be changed, comma, the new object to replace the old element. Note that set method returns the replaced object. ArrayLists can be traversed just like regular arrays using while, for, and for each loop. The only difference is using the correct ArrayList methods instead of array methods. ArrayLists are still susceptible to array index out of bounds exceptions. While traversing ArrayLists and removing elements, remember to modify your loop variables and/or body accordingly, or else you will skip over certain elements. Removing an element shifts all other elements to the left, and after incrementing your loop variable, you will skip one or more elements. When handling for each loops for array lists, you can't remove or add any items because a for each loop doesn't use an index. Attempting to modify an array list during a for each loop will result in a concurrent modification exception.
Searching is looking for a particular value or values in a data structure. Sequential or linear searches look through an entire data structure from start to finish and look for a target value. In terms of arrays, this means starting from index 0 to the final index, examining each element and determining if it equals the target. If nothing is found, the search should return some value indicating the target couldn't be found. This can be done with a method containing a for loop beginning at index 0 and ending at the final array index, examining each value, returning some value to indicate if the target has been found, or else returning a value to indicate the target couldn't be found, like -1. To determine the maximum runtime of a searching or sorting algorithm, we use the big O function. The function big O of some parameter n describes the limiting behavior of an argument as it tends towards a particular value or infinity, or, for our purposes, the maximum runtime of an algorithm. Linear searches have a maximum runtime big O of n, where n represents the number of elements in an array. As suggested by the linear search's big O function, linear searches can be incredibly inefficient for large lists. Other search algorithms like the binary search can be far more efficient. The binary search first examines the middle of a sorted, ordered from smallest to largest array, and sees if it equals the target value. If the middle value is higher than the target, the algorithm examines the lower half of the array and repeats this process until the array can no longer be divided. If the middle value is lower than the target, the algorithm examines the upper half of the array and repeats this process until the array can no longer be divided.
To determine the maximum runtime of a binary search for an array of length n, we must ask, how many times x do I need to have this array to get to the last element? Another way of asking this question is, to what power x should I raise 2 by to get n? Solving for x, we find that it equals log base 2 of n. So the maximum big O function for binary searches is log base 2 of n. So for an array with 600 elements, it would take you about 10 divisions to get to the last element, or log base 2 of 600 rounded up to the nearest integer, which may be also notated with the ceiling function, written as ceil of some parameter. In order to use binary search, however, we must first sort our arrays using even more algorithms. One type of sort is called the selection sort, which begins at index 0 and looks for the smallest item in an array. Once the smallest item in the rest of the array is found, the element at the current index is swapped with the smallest element. This process is repeated until the second last element of the array, or at list.length -2, at which point the last element will be the greatest element of the array and hence the array will be sorted. Selection sort uses nested for loops and has a maximum runtime of big O of n squared, so it is not efficient for large lists. Meanwhile, the insertion sort inserts the next unsorted element in the already sorted part of the array by moving larger values to the right of the array. It begins at index 1, loops through the entire array, and has a maximum runtime of big O of n squared. Two-dimensional array is an array that has rows and columns. The rows are the horizontal elements and the columns are the vertical elements. 2D arrays are objects useful for representing real-world entities like movie theater seats, classroom seats, spreadsheets, or game boards. Java treats 2D arrays as an array of arrays. A 2D array can be handled in row major order when all data is stored row by row. You can think of this as a vertical line of boxes running down, each one being an indexed row beginning at 0. Each box is actually an array that extends outwards horizontally, each extension being a column of the row. In row major order, the rows are treated as the outer arrays and the columns are treated as the inner arrays. In column major order, imagine drawing a horizontal line of boxes, each box being a column index. Each box may be extended downward or vertically, each extension representing a row of the 2D array. In column major order, the columns are treated as the outer arrays and the rows are treated as the inner arrays. Treating your 2D array as a row major order or column major order array depends on what algorithm you use on it. For beginners in Java, you will usually use row major order. Ragged arrays are 2D arrays whose inner arrays have different lengths.
To declare a 2D array object, type the variable type of the array, followed by double brackets and the 2D array name. To initialize an array object without initializer list, continue this format by typing equals new variable name and 2 square brackets. The first square bracket contains the length of the rows, the second square bracket contains the length of the columns. Remember that both start at 0. When a 2D array is initialized in this format, all elements are assigned the variable type's default value. When initializing 2D arrays through initializer list, declare the 2D array as previously stated and follow it with an equal sign and a set of curly braces. For every row you add in the 2D array, add another set of curly braces within the main curly brace. Each nested curly brace will contain the column values, each value being separated by a comma. The outer curly braces act as a net for containing each nested curly brace, which is a row, and each nested curly brace contains the column values. To access or modify an element from a 2D array, retrieve the value by typing in 2D array name and 2 square brackets. The first square brackets containing the element row index and the second containing the column index. To find the 2D array's number of rows, type 2D array name dot length. To access the length of a column at row R, type 2D array name, then a set of brackets containing R, then dot length. If all array columns have the same length, then you can just use 0 instead of R. Note that the length here is a field, so you don't need to include parentheses like with the ArrayList size method.
To traverse a 2D array in row major order, we must loop row by row, and for each row, we loop column by column. Let R denote the row number, C denote the column number, and array name denote the 2D array we traverse. Using a generic nested for loop that performs a full traversal, our outer loop header is written as for open parentheses int r equals 0 semicolon. R is less than array name dot length semicolon, r plus plus close parentheses. We move to our inner loop header, written as for open parentheses int c equals 0 semicolon. C is less than array name, followed by square brackets containing r, followed by dot length, and then a semicolon. C++ close parentheses. From here, we add to the bodies of the inner and outer loop to modify and or access the array and change the inner and outer loop headers if we wish to traverse only certain parts of the array. For column major order traversals, reverse the inner and outer loop headers from the row major order traversal and modify the loop variables accordingly. We can also use nested for each loops, only applicable when we don't want to modify any 2D array elements. The row is marked by some dummy variable and is treated as an array object. We traverse through each row like an array by adding a nested for each loop that has a dummy variable for the column number to be accessed within the row. Let row var be the dummy variable for the rows, call var be the dummy variable for the columns, and array name be the reference of our 2D array of type var type. To traverse this array using for each loop, write the outer loop header as for open parentheses var type square brackets, row var column array name close parentheses. Write the inner loop header as for open parentheses var type var row var close parentheses. From here, modify the loop headers or loop bodies depending on your algorithm scope. Most regular array algorithms can be applied to 2D arrays by correctly setting up your loops, including sequential/linear searches.
Another fundamental principle of object-oriented programming is inheritance. In Java, classes inherit attributes and behaviors from their parent classes. A class inherited from is called a superclass or parent class. A class that inherits is called a child class or subclass. A class that inherits from its parent class is a kind of type of its parent class. This is called an is-a relationship. A subclass called chocolate may inherit from a superclass called sweets because a chocolate is a sweet. Let a generic superclass be denoted by A and its subclass be denoted by B. The regular header for class A is public class A. For class B to inherit class A, the header is written as public class B extends class A. Java classes can only and will always inherit from one class, but parent classes can have multiple subclasses. If you leave off the extends, then the class will inherit from the object class, part of the java.lang packet. Inheritance allows us to generalize and specify our code. When several objects can pull attributes and behaviors from a parent class, we use inheritance to generalize our code so as to not reuse it. Each subclass then gets its own unique attributes and methods, hence using generalization to enable specialization. Some classes have a has-a relationship, in which an object of one class contains a reference to one or several other classes. For example, a student is a person, and they have an ID, but an ID is not a student. A student has a relationship with an ID, but an is-a relationship with a person. Only use inheritance for is-a relationships, which can be determined by using the is-a substitution test. Is a computer mouse a type of gadget? Yes, so a mouse class would inherit from a class gadget. Is a pen a type of ink? No, but a pen has ink, so a pen class would have a has-a relationship with an ink class. Subclasses can access their superclass's public methods and inherit their superclass's instance variables, but cannot modify them directly without using the superclass's constructor, which is done with the keyword super. Super is called in the subclass's constructor, which is done by typing super open parentheses and then a list of arguments following the order and type of the superclass's constructor, followed by a closed parentheses and a semicolon. This must be placed in the very first line of the subclass constructor. When a subclass object is created, the superclass constructor is called and initializes the inherited instance variables that only the superclass can access. Recall that classes that don't have written constructors will get a default no-argument constructor. This constructor initializes all instance variables to the default values of their type and implicitly calls the superclass's no-argument constructor. So you can only write a class with a default no-argument constructor if its superclass has a no-argument constructor. You may explicitly write a no-argument constructor in one class and call it using super in its child class. The super keyword works through a chain, winding upward in the inheritance hierarchy all the way up to the object class. Here, the object class constructor executes, and then the subsequent subclass constructors execute, one by one, all the way back down to the last subclass.
Overriding a method is a process of modifying inherited method. We call that subclasses may only inherit public methods. To override a method, the subclass must copy the superclass's method signature, and the body of that method will be modified in the subclass. Thus, when you create an instance of the subclass and call the method, it will call the overridden method instead of the superclass's method. Overriding a method is different from overloading a method. In method overriding, the method signatures are the same but are in different classes and have different functions. In method overloading, several methods have the same name but have different return types, numbers of parameters, or types of parameters. Child classes may also inherit their parent class's getter and setter method, which can be used to display or modify the child class's instance variables that are only accessible by the parent class. The super keyword can also be used with methods. If you want to override a method so that you perform the exact same superclass method but add onto it in the subclass method, type super.method name open parentheses arguments close parentheses in the overridden method. This will execute the superclass's method and then continue the subclass method of what you have added to it. Inheritance method calling works because objects keep references to the classes that created them. If a class method isn't found in the referenced class, it will move upward in the inheritance hierarchy, find where that method exists, and then execute it. If a subclass object calls a subclass method which calls a superclass method, and the superclass method contains another method with the same signature as another subclass method, i.e. the subclass overrode the method, then the overridden method in the subclass will be called from the superclass because the object reference is to the subclass. The inheritance hierarchy is like a family tree, except all children always have one parent. The parent of all classes is the object class at the top of the hierarchy. These hierarchies help generalize our code. We can generalize our code further by having superclass object references hold subclass objects. For example, a strawberry cake can generally be referred to as a sweet. However, we can't reference all sweets as strawberry cake, so you can't have a subclass reference its parent class. Having superclasses reference their subclasses makes it so that superclass parameters can take any one of their subclasses instead. For example, a sweets method that has a parameter for the sweets object can pass in a strawberry cake or any other type of sweet. This also works for all types of arrays. All subclasses can be stored in an array of the parent class's type. An array of sweets can contain strawberry cake, chocolate, and all sorts of other sweets because they are all subclasses of sweets.
The last fundamental principle of object-oriented programming is polymorphism, which literally translates to many forms. The method that gets called at runtime depends on the object's type. In Java, an object has a compile time type defined by the variable type of an object's declaration, and a runtime type defined by the type of class that creates the object placed after the new keyword. At compile time, the compiler checks that the declared type has all the methods or inherits the methods it uses in the code. If it doesn't, then you will receive a compile time error. If it does, then at runtime, the execution environment checks if the given method is in the runtime type, and if not, it moves up the inheritance hierarchy. Because objects can take a declared type and a runtime type, which allows us to generalize and specialize our code by having subclasses reference their superclass and override methods. These objects are polymorphic. The same code for these objects have different results, hence the meaning of many forms. Superclass references may be cast to their subclass references in order to perform specific subclass methods for objects that have a superclass reference. Casting from the superclass to the subclass is called downcasting, and casting from the subclass to the superclass is called upcasting. All classes inherit the toString and Boolean equals method from the object class. These methods are commonly overridden. An object using its toString method may call its parent class's toString method, using the super keyword to first print out superclass information about the subclass object and then more specific subclass information. As for the equals method, the general formula for writing an equals method is as follows. Write public boolean equals open parentheses object other close parentheses for the method head. We use object as the other type here as a parameter because it generalizes what we can put into our parameter. From here, modify the method body depending on the criteria needed for your objects to be equal.
Recursion is essentially when a method calls itself.
Consider a void no argument method called method name. In method name calls itself through the command method name parentheses semicolon. Also, consider an integer method with a parameter list param list called int method. Int method may call itself by returning int method open parentheses param list close parentheses semicolon. We are still recalling the method, but are now using the return keyword because the method has a return type.
If a method keeps calling itself and there's no stopping point to the recursion, then the result is an infinite recursion and never-ending recursion. Recursion breaks down big problems out of repeating structures into solvable small problems. This is useful for dealing with things like binary trees, files, fractals, factorials, and even Fibonacci sequence. Recursive methods require a base case that halts recursion, and they may have several base cases. The base case is usually within an if statement and is the simplest answer or result from a recursive method.
For example, consider a recursive factorial method called factorialX, which takes a parameter x and computes x factorial, the precondition being that x is not less than 0. Recall that the simple definition of a factorial effects is the product of all integers from 1 to x, with both 0 factorial and 1 factorial being 1. For our recursive method, if x is 0, our simplest possible value of x, we return 1. This is our base case because we aren't performing any recursion and are returning a specific value, and it is contained within an if statement. If x is not 0, hence this next part will be an else statement, then we return x times factorial x of x minus 1. Here, we return our current x times the recursive call of factorial x of x minus 1. Because this else statement calls the method again, it is not the base case. Once factorial x of x minus 1 is called, this process repeats itself, all the way down until x becomes 0 from repeated decrementations, at which point the method will return 1. This is done through the call stack, which keeps track of the methods called since the main method's execution. The method stack adds and removes methods from the top of the stack like a stack of cups. When method y calls method z is placed at the top of the call stack with information about where method z was called from, i.e. method y, to let the runtime environment know where to continue execution after method z has been executed. Once method z has finished, it pops off the call stack and method y continues its execution. When a method calls itself, the current method execution pauses and a new method is added to the call stack. Each of these recursive calls contains its own unique parameters and local variables, which change during each recursion along the call stack. Going back to our factorial example, once we reach the base case of 1, which is called by factorial x of 0, we pop this method off the call stack and continue the execution of factorial x of 1, which multiplies the result from factorial x of 0, or 1, by 1. The result is 1, and once factorial x of 1 returns 1, we move to factorial x of 2, which returns 2, and the method pops off the call stack, repeatedly occurring until we make it back to the original method call, in which we would return x times x minus 1 all the way down to 1. Note that any recursive solution may be written as an iterative process, like a for or while loop, and may be used to traverse strings and or arrays. One useful application of recursion is searching and sorting. Recall that the binary search continually eliminates halves of data until the target value is found, and is only applicable when data is sorted. The recursive binary search method differs from the iterative solution in that it also takes the start and end values as method parameters and modifies them by each recursive call. Recursion can also be applied to sorting. For example, recursion can be used in the merge sort. The merge sort works like this: divide the data into halves, recursively sort each half, and merge the halves back together to produce a single array. In short, it is a divide and conquer algorithm. You've come to understand the fundamentals of Java, as well as the four main principles of object-oriented programming: abstraction, encapsulation, inheritance, and polymorphism. You too can become a computer science master. Just don't forget the semicolon. Do you know? If you do know, then you do not know. If you do not know, then you are certain to not know. Are you sure of it? Socrates was surely not aware. There is a quote from Socrates. Here it is for those of you who are unaware. One thing only I know, and that is that I know nothing. Socrates says he does not know, and Socrates cannot know? No, Socrates does not know. This is because he says he does not know. If he does not know, then how should we know? No, we do not know. In order to know, we must know more than Socrates, but Socrates does not know? So are we less than knowing? We are not known, and that is to ourselves. No, again, you are unaware. Beware, the unknown is you. You are you. We are we. And everything is not known. Unawareness is the main element for you, and we do not know.
But if you know nothing, you cannot know something, and therefore you cannot know anything, so therefore you should not be able to write or speak. And if that's the case, then how did Socrates know that he did not know anything? How did he write or tell this quote if he knew nothing? It shouldn't have been possible for him to do this without knowing how to write or speak. He must know something.
Sorry, but you don't know.
But in that case, you wouldn't know either, so then how would you know that I do not know?
The first proton did know that we did not know, knowing that it did know, informing us that we do not know that we do not know.
The first nitrogen and carbon did not know that we did not know that we would know that they knew that they didn't know that they were going to blow up and make the universe. And the universe did not know that it would continue expanding. And the solar system did not know that it would continue granting. Life, that is. And it did not know how it was made or where it was. The sun was made by nitrogen, and it did not know that we did know that we would not know that we knew that they didn't know that they were going to make the sun. Then the earth appeared, although it did not know how, and then the life appeared in life, and it did not know that we did not know that we would know that it knew that they didn't know that it was going to exist. And then life evolved, although it did not know that it would know that it did. Then the humans did not know these things until they knew that they did not know about it, and decided that they needed to know what those things were. The unknown things were now known, but what was not known was who told me to say all these things. But eventually we did find out that the first proton did know that we did not know that it knew that it did not know, informing us that we do not know that we do know. You see, we actually do know that we do not know that we know, and not that we didn't.
You can't speak without having legs. You can't walk without learning how to talk. You can't be without being in Nihon. Nihon, for context, is the Sunrise Kingdom. But Tokyo isn't a city. It is the East Imperial capital. No, Tokyo is in Kyoto. Kyoto was Tokyo, but it isn't Tokyo now. It is Kyoto, but Tokyo was not Kyoto before it was Tokyo. If you live in Osaka, chances are you can talk. But the walking and the talking literally translate to talking while you are in the state of the action of walking. You aren't walking while you are talking in Nihon, the Sunrise Kingdom. You are in the state of being in Nihon, but you have to walk and talk at the same time. Obviously, Osaka isn't the propaganda herd, though be careful. If you can't walk while talking, you won't see. If you can't see, you can't move your arms for the lobsters on the Kyoto coast. Tokyo, for clarification, does currently exist at this time. Tokyo is a city, not a planar. The disparity of light through several thousand miles does indeed leave a gap. He's sipping on the tea of Nihon, the Sunrise Kingdom, and you cannot walk and talk. Cry. Cry that you can talk in Tokyo and walk in Kyoto. You're not from Osaka, you are Osaka. Osaka is what walks and talks, and Osaka is Tokyo and Kyoto, but Kyoto is not Tokyo. He proceeded to walk in Nihon, the Sunrise Kingdom, for many days. Though he could not talk, "Arigato!" he screamed while walking.
I'm confused. Does Kyoto talk with Nihon?
No, Kyoto does not talk with Nihon. It instead speaks with it. There is a very big difference between talking and speaking.
If a flower blooms, then the flower is theoretically a bloomed flower. Without it being bloomed, it can't be a bloomed flower. Of course, a flower goes through different biological processes to get through to this bloom. A bloomed flower is a flower you know has bloomed. So can a flower bloom without blooming? Of course, without any knowledge, a flower could bloom without blooming. The bloom of a flower is based on the definition of what blooming is. To bloom is to bloom, and that is the definition without the knowledge of what blooming is. Everything, like a blooming flower, has a definition. The location and climate of where the flowers bloom could also play into a flower blooming depending on what a blooming flower is and whether it has bloomed even though it may have not bloomed. The definition of blooming is infinite as long as the line. A line in basis is infinite, but applied to these flowers it's an infinite line on the floor. When the flower blooms, infinity can bloom as well as negative. The definition gives the context. A blooming flower can bloom in the sunlight while not being bloomed in the moonlight, but the flower can bloom in the moonlight and not bloom in the sunlight. The bloom of a bloom is what blooms in the bloom, but the bloom cannot bloom without blooming unless it does not bloom while not blooming while blooming. The bloom is what blooms, however, it doesn't have to bloom, but the flowers in the sunrise kingdom have bloomed. ありがとうございます。